One of the most important applications of second-order linear differential equations is the mass spring system. So that's what we're going to talk about today. So let's recall how this works. So we actually introduced this in a previous lecture. I'm just going to draw our picture again. So we have a mass here. This is a mass M, and that mass is attached to a spring. And we also had another device here called a dashpot. And essentially what that dashpot did, if you'll remember, is it applied a force that was proportional to the velocity of the object, but acting in the opposite direction. So it would try to sort of slow the movement of the mass. And so I'm not going to redrive the differential equation here, but if you'd like to see that, you can go back to the very first video on second-order linear differential equations. Well, let's define our variable first. So we'll call it x. So maybe there's some equilibrium position, and we want to study the position of the block at any time. So the equilibrium position is just where the mass would sit on its own and do nothing. So our differential equation was mx double prime plus gamma x prime plus kx equals 0. Where that gamma is what we call the damping coefficient. That's coming from the dashpot. And this k here is the spring constant. And before we go any further, you might be wondering, when am I ever going to use this picture here? And you might not ever have this picture sitting around, right, where you have a mass attached to a spring and a dashpot. But actually, this picture is in a lot of things you use every day. So, for example, a car suspension system has a device that's very much like this. And the other point is, there are many different systems that can be modeled by this differential equation, even if it doesn't physically have a mass and a spring. So it could be, for example, a building shaking in an earthquake. You can often model things like that as a mass spring system, even though there's not physically a spring there. But you can still talk about a spring constant and a damping coefficient of the motion. And even examples like a RLC circuit, like we saw in the previous lecture, has nothing to do with springs, but it turned out we got the same differential equation. So you can actually think of the charge on a capacitor in an RLC series circuit as a spring, a mass attached to a spring with a damping device. So very important differential equation. Often in practice, the picture is actually not going to look like this. It'll actually be oriented vertically. For example, in the car suspension system. So let's talk about what to do in that case. So vertical orientation, and it turns out that it's a little bit different. Well, I should say it's a little bit different, but in the end, you actually end up with the same equation. But I want to show how that works. It's just a little bit subtle. Okay, so we have our dashpot and we have our spring, and let's say we don't attach the mass yet, and we'll call this position here y equals 0. Now let's draw another picture where we do attach the mass, and that actually stretches the spring out a little bit, as you can imagine. This is just due to gravity. So we've attached our mass here. So here's my mass M. And let's say this new position is L. Okay, so that's where the mass is after I attach it. And before I attach it, the end of the spring was just right there. Great. Okay. So so first thing I want to point out here is you can actually, by measuring this L, you can actually determine the spring constant K, even if you didn't know it in advance. And the reason for that is, let's assume that this picture is just at rest. So this is at rest. Well then, what are the forces acting on this mass? Well, there's a downward force due to gravity. We didn't really have that in this first picture. Well, I mean, technically we did have it, but there was a normal force that was counteracting it. So here we have a downward force due to gravity, and we have an upward force due to the spring, right? So it's negative K times the displacement, which is L, right? That's the displacement from the equilibrium position. And there's no force from the damping device because the object is at rest, right? We only have a force from the damping device if the object is moving because it's proportional to velocity. And so what do we have here? We have mg minus KL is 0. These forces balance each other out. But m, g, and L are known, right? We can measure L, so we can just solve this for K. mg equals KL, so K is going to be mg over L. So that's pretty cool. We can actually figure out the spring constant just by sort of hanging a mass from the spring. So that's how to get the spring constant if we don't know it. But let's actually try to write down a differential equation in this case. It's going to look a little different than this, at least when I first write it down. So what do we have? We have what is our net force? Oh, okay, so now we'll assume that, maybe this mass is at position Y. Doesn't necessarily have to be at position L, right? So it's now at, this position Y, and we want to study this function Y of t. Okay, so the vertical position. And it could be moving, right? Or it could be sitting still, but what is our net force going to be in any situation, right? So so again, we have a downward force due to gravity. That's mg. And we have a damping force. That's minus gamma times the derivative of y. So minus gamma y prime. And of course, we also have the spring force. So that's minus k times the displacement y, right? So displacement from y equals 0, which is just this function y of t itself. And by Newton's second law, this force is going to induce an acceleration, so that will be m times y double prime. And so we have this differential equation here. And I'm going to just write it in the usual linear form. So we have m y double prime plus gamma y prime plus ky, and that's going to equal not 0 in this case actually, but mg. And so this is actually an inhomogeneous differential equation, right? Because we have something on this side that's not just 0. I mean, it is a constant, right, which is pretty close to 0, but it's still not 0, so we call it inhomogeneous. But I want to point out a standard way that we can actually change this equation into this equation, and that's by doing a change of coordinates. And it's a very natural change of coordinates, so it's nothing crazy. The main idea is, once the mass pulls a spring down to this position L, why don't we just call this 0, right? So I'll have a new y that, okay, maybe I'll call it ye for equilibrium, okay? So I want this ye to be 0 right here, where the old y is L, right? So in other words, ye is going to be y minus L. I need to subtract that offset L, because I want this to be 0. Okay, great. So now I want to change variables from y to ye. So I need to take derivatives and second derivatives. Well, the derivative is just equal to y prime. The L goes away. And second derivative of ye is just equal to second derivative of y prime. So let's plug it into the differential equation. So we get m y double prime e plus gamma y prime e. E is just a subscript. Plus k times, here it's a little different. We have y minus, sorry. I actually need to solve, so I have y here, so I want to solve this for y. So y is actually equal to ye plus L. So I have ye plus L. And that's going to equal mg. Okay. And so m y double prime e plus gamma y prime e plus k ye plus kl equals mg. Let's move the kl over to the other side. So we just get mg minus kl. But do you see what's going to happen here? You see what's going to happen here? Look up here, right? mg minus kl is 0. So this side is actually just 0. And what we have is the exact same differential equation up here, right? So I just call this ye the new y. And I have the exact same differential equation. I just have to keep in mind that I need to take this the equilibrium position with the mass attached, right, to be my 0 position. Okay, and if I do that, I don't have to worry about this mg. In other words, it already accounts for the gravity if I just call this position the equilibrium position. So that's the whole point of that. Basically, you can just use the same differential equation, whether it's the horizontal setup or the vertical setup. Okay. So how do we solve the mass spring equation? So let's just let's do solving this equation. So solving, I'll just call it my double prime plus ky prime plus, sorry, not ky prime. That should be my damping coefficient, not my spring constant. This thing's not working too well. There we go. This should be the damping coefficient, gamma. Here's my spring constant, ky equals 0. And I also want to keep in mind that this is not like the differential equations we've been solving in the previous few lectures. Well, I mean, actually it is. It's very similar. But we have an added restriction here, which is that all these coefficients are positive numbers. So, well, okay, certainly m and k are going to be positive, or else we don't have a mass and we don't have a spring, so we can't even talk about it. And then we'll let gamma be possibly 0, but cannot be negative. Right? So all of these are not going to be negative. And let's keep that in mind in our analysis. So how do we solve this? Well, we know what to do. We guess e to the rt because it has constant coefficients. And we get our characteristic polynomial mr squared plus gamma r plus k. This just comes from plugging in our guess and then canceling out the e to the rt factors. Okay, so there's our characteristic polynomial. And what are the solutions? Well, let's use a quadratic formula. So it's negative gamma plus or minus the square root of gamma squared minus 4mk over 2m, right? Just using a quadratic formula there. And what is the most important quantity here? It's actually this discriminant. So the discriminant is this gamma squared minus 4mk. And we saw in the previous lecture that this is really what's going to characterize the behavior of the solutions. In particular, we have three cases. Case 1, the discriminant could be positive, in which case we have two real roots. The discriminant could be negative, in which case we have two complex roots. Or the discriminant could be 0, in which case we have one repeated real root. Okay, so let's look at those cases one by one. Let's go ahead and go to a new page. Case 1. Case 1, we're going to have our discriminant be positive. Gamma squared minus 4mk, positive. And this is going to be called, so this has a name, it's called the overdamped case, or overdamped motion. It's too much damping. Remember, gamma is a damping coefficient, so as gamma increases, we're more likely for this to be positive, right? And eventually this will become positive if we increase gamma enough. So if this is positive, it means that gamma squared is large relative to 4mk. Okay. All right, so we have our discriminant positive, which means we have two real roots, right, of the characteristic polynomial. And what are those roots? Well, the first one is just these two right here, and we know they're real. So we have a negative gamma plus square root of gamma squared minus 4mk over 2m. And then our second root will be the same thing, but with a minus sign here. Gamma squared minus 4mk over 2m. Those are our two roots. And our general solution, remember our guess is e to the rt, so our general solution is just going to be c1 e to the r1t plus c2 e to the r2t, just like we've done in the previous lectures. Okay, so how is this different than what we did before? Well, we know that m, gamma, and k for the mass spring system, they're all positive, including gamma, right? Or else we certainly can't have this be positive. Well, it turns out that implies, actually, that R1 and R2, both these roots, both of them are negative. Okay. Can we see that? So let's look at these formulas. Well, I think if you look at R2, I think it's pretty obvious that this is going to be a negative number. Because, remember, they're all positive, but then this becomes negative here. And I'm subtracting something positive, so I'm even more negative. And I'm dividing by a positive, that's going to be negative. It's maybe not so obvious that this one here has to be negative. So let's look at that really quick. So R1 is negative gamma plus square root of the discriminant over 2m. But, okay, so then if you look at this thing in the square root, this number in the square root is definitely less than just gamma squared on its own, right? And so this number here, right, I'm adding, so in other words, this is less than negative gamma plus if I just had the gamma squared alone. Right, because this one I'm adding this gamma squared. This one I'm adding gamma squared minus 4mk, something smaller, right? So this one is going to be larger. And it will be strictly larger, right? I'm not putting a less than or equals here. I'm putting just a less than. And And that's because m and k are positive, right? So I'm definitely subtracting something here. This is definitely going to be smaller than this one here. But you see what we get over here is just 0. Right? So we just proved that R1 actually has to be smaller than 0. So it's negative. So these are actually decaying exponentials. Okay. And so in particular, we can understand something about the behavior of these solutions. Their limit, as t goes to infinity, is 0 for all solutions, regardless of C1 and C2. Okay. Here's a typical graph of something you can get. Let's try to sketch what the overdamped case looks like. So here's just one example. Maybe we start here and we're pushing the mass in pretty fast, and so it actually snaps back past the equilibrium position, but then it kind of just slowly returns to the equilibrium. So nothing too exciting. That's an example of overdamped motion. In particular, we have no oscillations. Okay, so that's the overdamped case. Okay, let's look at the next case. So case 2. Case 2, our discriminant is going to be less than 0. So our discriminant will be negative. And I would actually like to break this up into 2 subcases. So this is going to be subcase 2a. Okay, what if we have no damping whatsoever? In other words, undamped. Okay, well then this is certainly going to be negative, right? So this is a subcase of case 2. If this is 0, then we have minus something positive, which is definitely a negative number. Okay, so in this subcase, well, what do we have? Our characteristic polynomial actually just looks like mr squared plus k equals 0. And so what are our roots? R is going to be plus or minus the square root of negative k over m. You solve for r there. But wait a second. So yeah, I have negative k over m. That can be written as plus or minus I times k over m. Right? Because k and m are positive. So this is a negative number in the square root. So this is an imaginary number here. Okay, so I have imaginary roots. We know what to do in that case. What we do is we just take one of them. E to the, let's do the plus I square root of k over mt. Remember, because our solution is e to the rt. And then we'll use Euler's formula. So we get cosine square root of k over mt plus I sine square root of k over mt. Okay. And then we take our real and imaginary parts, and those are our 2 linearly independent solutions. So I should go all the way up here. Okay. So just to make this a little simpler to write, let's let omega be square root of k over m. Omega is commonly used to refer to an angular frequency, and that's exactly what we have here, right? It's cosine of something times t. That something can be interpreted as an angular frequency. So I'm just going to call that omega. And then our general solution is C1 cosine omega t plus C2 sine omega t. Okay. And so here in this case, so here, this omega, it has, like I said, it's called the angular frequency. Okay. And then we define the period to be 2 pi over omega. This is the period. And the period is actually a really useful concept because you can see it really easily from the graph. So here's a typical graph of undamped motion. It's basically what you'd think. It's just a sine wave. Mass going back and forth and back and forth. It never actually loses amplitude. So here's t and here's y. And the period is a really useful concept because you can just see it. It's the distance from one crest of this wave to another crest of this wave. This is called the period. Okay. Okay, well, why am I drawing this as a sine wave? Because don't we have a sum of a cosine and a sine? Might that look different? Well, the answer is no. We talked about this in a previous lecture. We can actually write, so we can write this sum. So we can write y of t as a single sine or cosine. A single, let's do a cosine. So we talked about this, but I'll recall, actually what these numbers mean. So y of t, we can actually write it as a times a cosine with the same frequency, but possibly shifted. Right? And let's just recall what these were. So we derived this in the lecture on a lecture called Complex Roots of the Characteristic Polynomial. We got formulas for a, which was c1 squared plus c2 squared, then take the square root, where c1 and c2 are these. And this phi is, it turned out to be the arctan of c2 over c1. Okay. And this a, so a is called the amplitude. Okay. And the meaning of that graphically is this height here. So this is the amplitude. So the amplitude and period, you can see really easily from the graph. You can get omega if you have the period, right? Because you can solve this for omega. Omega is just 2 pi over the period. So you can get a lot of information just from a graph of the motion, just from observing the motion. So yeah, A is called the amplitude. And this case in general is an example of simple harmonic motion. Right here. Let's look at something a little more complicated now, which is so we'll have what are we on? We're on a subcase 2b. So subcase 2a was no damping. Now let's have damping. But let's recall our discriminant is still negative, but we're going to allow some damping. So this will be positive. This will be positive, but it won't be too positive. If it were too positive, then this whole thing would become greater than 0, right? So we still need gamma squared to be less than form k. Okay, what is this called? This is called, so there's some damping, but not enough to make this positive. So this is called the underdamped case. Okay. So what have we seen so far? We've seen overdamped, undamped. Here's underdamped. Let's write out our roots of the characteristic polynomial again. Gamma squared minus form k over 2m. Okay. What can we do with this? So we know that this thing inside the square root is negative, right? So I'm going to try to make that obvious in the way I write it. So yeah, in other words, if it's negative, we have an imaginary number here. So let's try to introduce an I. So I'm actually going to factor out a -1. So I have a square root of -1 times a square root of, so I have an I times a square root of Now it's 4mk minus gamma squared, right? I factored out that -1 and I wrote that as an I instead. I still have over 2m. Now let's write this in a plus bi form. So we have gamma over 2m, negative gamma over 2m, plus or minus I times square root of 4mk minus gamma squared over 2m. Okay? And so this is a plus or minus ib. And if we recall, the solutions are going to look like e to the a plus ib times t, and we need to take the real and imaginary parts of that. We end up getting products of exponentials and cosines, and exponentials and sines. But before I write that out, so recall what this b actually ends up inside the trigonometric functions, right? Because we have e to the at cosine bt plus e to the at sine bt. We can multiply them both by arbitrary constants. So because of that, I'm going to define this right here. I'm gonna call that omega, because that's exactly the coefficient, that's exactly the factor that ends up inside the trig functions. So I'm going to call omega 4mk minus gamma squared square root over 2m. Okay, just like we did before. So notice here we have a much more complicated expression for omega. Here we had a much simpler one. And that has to do with the damping, right? So there's some damping here. And let's just use the work that we did before. So y of t is c1 e to the at, so negative gamma over 2m. I guess I could have renamed that something too, but oh well, too late for that. Times cosine omega t, cosine bt, we're calling it b omega, plus c2 e to the negative gamma over 2m t sine omega t. Okay. So that's our general solution. And here, we can guess what omega is going to be called. So omega is called, so we'd like to call it the frequency again, or the angular frequency, but we don't want to confuse it with this case, right? Because it really is a different formula, and we have different behavior. So we actually call omega the quasi-frequency in this case. So when you see quasi-frequency, that's referring to this underdamped case. And then now you can probably really guess what this t is called, 2 pi over omega. If omega is a quasi-frequency, then t is the quasi-period. Okay. Let's look at a graph to see how we interpret these. So, all right, what does the underdamped case look like? Well, what we have is we have decaying oscillations. Okay, so we have oscillations, but this e to the negative something t, right? This is negative because, again, gamma and m are positive. So we have oscillations, but they're decaying, like this. So it's t and y. And this right here is e to the negative gamma over 2m. Well, actually, it's not quite that. Getting a little ahead of myself. Okay, but the point is we have decaying oscillations, and here's what the quasi-period looks like. Okay, so it's from crest to crest again. And to really figure out what's going in this graph, let's also note that we can write this in this form. So we can write this as a single cosine or sine. So I can factor out this exponential, and then I just get the same thing here, right? I get a c1 cosine plus c2 sine. So we can actually write this as a e to the negative gamma over 2mt times a single cosine, for example. Where again, a and phi are the same formulas here. Right, so a is square root of c1 squared plus c2 squared. Although it doesn't really make sense to talk about the amplitude here, right? Why doesn't it make sense? Well, just because the oscillations are decaying, so the amplitude is actually changing. If we want, we can think about this whole thing as the amplitude. So this is really what I should have written there. This blue curve there is a e to the negative gamma over 2mt. Okay. Yeah, so we have decaying oscillations. That's the underdamped behavior. Okay. For all solutions, what can we say about the limit? Limit of our solution as t goes to infinity. Well, this decaying exponential is going to ensure that all solutions will decay to 0. Okay, so if we had a mass on a spring, it would go back and forth, but the oscillations would get smaller and smaller until it basically returns back to the equilibrium position. Okay, great. So that's the underdamped case. And there's one more case. This is actually the most important of all of them, in a way. Even though it technically doesn't come up in practice, because it's sort of right on the razor's edge between this case and the underdamped and the overdamped case. What if this discriminant happened to be exactly 0? So we call that critically damped. If it's exactly 0. Okay. Well, what's going on? So we have our roots of the characteristic polynomial. I've already written it out so much, I'll just pull this one down. So here are our roots. If gamma squared minus 4mk is 0, we only have one root, and it's a double root. That root is negative gamma over 2m. Okay? This is a double root. And we know what to do for the solution in that case. So we learned in the previous video that the solution is going to look like the general solution. Will look like C1 e to the RT plus C2 t e to the RT. The same R. Negative gamma over 2n. Okay, so that's our general solution. And this is really important because it's a boundary case between two very different kinds of behavior. So there are no oscillations in this case. In fact, if you draw a graph of some of these, they essentially look very similar to the overdamped case. Okay. So technically there's a t here, but it's very hard to distinguish the graphs of critically damped and overdamped motion. So there's no oscillations. That's the key. But we're very close to having oscillations. So this is the boundary case. It's a boundary case between oscillations and no oscillations. Okay. So if we're on this case, but if we decrease gamma even slightly, right? So if gamma is decreased, even just a tiny bit, we have no oscillations, but we get oscillations if we decrease gamma. So we get oscillations. Okay. So that's what critically damped means. It's sort of right on the edge between the underdamped case, this kind of motion, and the overdamped case, which is just this kind of motion. Okay. So those are all the cases for a mass spring. What can we say about the limit of these solutions, by the way? As t goes to infinity. Well, we have decaying exponentials again. And technically t here, that's increasing, but the exponential always wins out against the polynomial. So this limit will go to 0, this limit will go to 0, so the limit is going to be 0 again. Right. So in other words, yes, the mass will eventually return back to equilibrium position. And that's true in every case except for this case, right? Except for the undamped, right? Where gamma was exactly 0. We had no damping at all. That's the only time that our block doesn't eventually return back to the equilibrium. Okay, so now that we've learned the theory behind the mass spring systems, let's try to basically synthesize everything that we learned today by solving a problem. So here's a problem that I have in mind. Okay, so we want to design a shock absorber for a car suspension system, kind of like I talked about at the beginning of the lecture. Car has a mass of 1,000. So, okay, our mass is 1,000. And then before we install the shock absorber, the car is actually going to bounce up and down with a certain angular frequency. Okay, so the undamped motion before the shock absorber is installed, it's going to have a frequency of 3 radians per second. Okay. And we want to determine a couple things here. So first, we want the minimum value of a damping constant that will eliminate the oscillations. Okay. And then when we choose that damping constant, so when we install the damping system, how high will the car rise when it hits a bump above its equilibrium position? And okay, so we want to assume the bump imparts a vertical velocity of 1 meters per second. So there's a lot to unpack there, and it definitely seems that this will be a multi-step problem. So our undamped motion has a certain angular frequency. And we want to figure out a damping constant to use. What don't we know? We don't know the spring constant. Doesn't say the spring constant. Okay, well, can we use this to figure it out, is the question. And so the answer is yes. You'll recall from the undamped case, what was our formula for the frequency? Our frequency ended up being square root of k over m, right? So what do we have? We have 3 equals the square root of k over 1,000. Okay, so if we square both sides, we get 9 equals k over 1,000, so k equals 9,000. So we just learned another way to figure out the spring constant, I guess, right? If we know the mass and we sort of let the spring go back and forth, and if we can measure the frequency, then we can also determine the spring constant. So pretty cool. But okay, so k, no longer a mystery, it's 9,000. Okay, we would now like to know what is the minimum value of an effective damping constant that can be used to eliminate the oscillations. That's the key. We want to eliminate the oscillations. Okay. Well, how do we do that? So remember, our discriminant was gamma squared minus 4mk. Okay? And so here's what I want you to imagine. I want you to imagine that gamma is initially 0, right, because we have undamped motion. And this is pretty large, right? It's very large, in fact. Okay, now imagine that we're increasing gamma, okay, from 0. So now we're increasing gamma, but because this is so large, this number is still going to be negative, right? And so as we're increasing gamma, we're now in the underdamped case. We continue increasing gamma until gamma squared minus 4mk is exactly 0, okay? Now we're in the critically damped case. So the underdamped case is associated with oscillations still, but we want to eliminate those oscillations. So we want to increase gamma until gamma squared minus 4mk becomes exactly 0. And then if we continue increasing gamma, this will now be positive, and we're in the overdamped case. But we don't want to be in the overdamped case because we just want the minimum value of the damping constant that can be used, right? We want to go just as far as necessary to eliminate the oscillations. So you want this critically damped case, okay? Well, now we know what to do, right? So gamma squared minus 4mk equals 0, so gamma squared has to equal 4mk. But what is 4mk? It's 9,000 times 1,000 times 4, which is 36 million, I guess. Okay, so gamma has to be square root of that, 6,000. So there's gamma. That's the smallest damping constant, damping coefficient that we can use that will eliminate the oscillations. Okay, and again, yeah, this corresponds to the critically damped case. That's what we want. Okay. What's the next part? So now that we installed this damping system, how high will the car rise above the equilibrium position? Well, that seems a bit tricky. So in order to do that, we're going to have to solve the differential equation, probably. We have to find the function y of t. And then I suppose we want to find a maximum value of y of t. We're going to have to maybe use some calculus to do that. But first, let's solve the differential equation. Well, what is our solution? So we're in the critically damped case. That's key. We have to know what case we're in order to write down a solution, right? Because the solution looks very different in all three cases. Okay, so let's go back to our critically damped case. So our solution is this right here. All right. Let's write that down. So here's our solution to the differential equation. So our general solution is C1 e to the negative gamma over 2m t plus C2 t e to the negative gamma over 2m t. All right. And do we have any initial conditions? Well, we're thinking of this as a vertical motion, right? The spring is it's a shock absorber for a car, which and so our car is going to be bouncing up and down vertically. So we can assume that as the car is just riding along, it's going to be in its equilibrium position before it hits the bump. So y of 0 is going to be 0. Y of t you can think of as the height of the car. The height of the car. And then y prime of 0 is 1, right? We're given that. Okay, so let's solve this initial value problem. First of all, what is negative gamma over 2m? I think we can just calculate that. Right, so it's negative 600 over, or negative 6,000 over 2,000. So that's just 3, negative 3. So y of t is actually just c1 e to the negative 3t plus c2 t e to the negative 3t. Let's use our first initial condition here. What does that tell us? It tells us that 0 equals c1 plus this term is going to be 0 because we're substituting in 0 for t. So c1 is 0. That's kind of interesting. That whole term just goes away. So let's update y of t. It's actually just c2 t e to the negative 3t. Okay. Now let's use this initial condition. So we need to take the derivative, and we get product rule here. All right, we have a t and an e to the negative 3t. So we have c2 e to the negative 3t plus minus 3c2 t e to the negative 3t. And now let's plug in this. So y prime of 0 is 1. What does that tell us? 1 is going to equal c2 plus, again, something that's 0. Right? So c2 is just going to equal to number 1. So y of t is 1 t e to the negative 3t. That's a very nice looking function there. So this is describing the height of the car. Okay? And if you graph this function, it might look a little something like this. And it's going to decay. Remember, this is going to go to 0. So t, y. What do we want to find? We want to find this right here. We want to find the maximum height of the car. And so how do we do that? Well, when we want to find the maximum value of a function, that's a calculus problem. The derivative is going to be 0 there. At least for a continuous function, yeah, the derivative will be 0 at a maximum. And so we first want to find this value of t that corresponds to this maximum, and then we'll just plug it in to find our maximum value. Okay? So we want to set our derivative of our function equal to 0 to find the so-called critical points. I suspect we'll just get one critical point, and that will be our maximum. So let's take the derivative. We sort of already did that up here, but it's going to be e to the negative 3t minus 3t e to the negative 3t. Okay. Now let's set that equal to 0. And I'll factor out this e to the negative 3t. And we get this. And we want to solve for t. Well, this term here is never 0. So this has to be 0. Which means t has to be 1/3. So here's 1/3. Finally, to find the maximum, we just plug 1/3 into our function. So we want y of 1/3. It's going to be 1/3 e to the negative 3 times 1/3, which is just e to the negative 1. So we get 1 over 3e. So that is the height that the car rises to after hitting the bump. I think it's pretty cool how the number e shows up there. Yeah, so this example was sort of a synthesis of a lot of the ideas from this lecture.